Yeah, hello everyone. So today we are going to see the second part of the sorting algorithm. So last week we have looked at from basic selection, insertion, bubble, and merge sort. This week we are going to look at quick sort implementation and the more interesting aspect called Radix Sort, which is a non-comparison based sorting algorithm, which usually comes in the radar of order of n. Uh, in a certain aspect out of n, the time complexity will be 8. So we will look at those aspects, how it works, and we will do the coding side by side. Okay, so let's start with the session. So let me, okay, so we will start with quick sort. So we this is one of the basic sorts among the few sorts. Then we'll go to Radix sort, which is a little. The concept is similar, but it goes a little bit uh, above this current based sorting algorithms. So it's a comparison based. It's quick sort is also comparison based sorting algorithm. So when we say comparison based, that means comparing between two numbers. Comparison between two numbers. That's how we usually tell. Okay. Now it's a divide and conquer technique. So merge sort also we have seen a divide and conquer where you take an array, you divide an array into half, then okay, screen is not visible. Okay, sorry. Thank you for informing. Start entire screen. Okay, it's not coming up. Just a minute. Okay. Yeah, I think you can see the screen now. I thought it was already there. Okay. Okay, so we are talking about quicksort, and it's one of the basic sorting algorithms, and it's a comparison-based sorting algorithm. That means we have to compare between two numbers to sort to make them in a particular order, be ascending, descending, or any other order. So it's a divide and conquer technique. So each will have a so it contains of three parts: divide, conquer, and combine. So this divide conquer technique is, again, you have to summarize. There will be a problem P which you're going to divide into sub problems, and you divide a sub problem to the extent where it can't be divisible more, and then you try to solve that sub problem. And the way you solve the sub problem, uh, you will start combining the solution till you get the proper answer. So that's how it is. And even in Mustard also we have done the same thing, that we divide the array into two parts, and then the sub arrays we divide again the sub arrays into two parts, so on till we get to a single number, and then we started comparing between single numbers and started merging them. Okay, so in quicksort also it happens the same, but here the approach is slightly different. Here instead of it's a in place algorithm, so it's in place, it contains in place sorting. In place sorting, that means no need to have an auxiliary space or extra space, you can call it, because in merge sort, if you have studied and remembered, for every subarray that we are creating, we have to keep it in a certain location. That that is the extra space that having. But here in quicksort, you don't need to have it. So how it starts with? So here there's something called a concept of pivot. So what is the pivot is, you select a number which can be the rightmost number, leftmost number of the array, or any random number, or a median. Okay, you select one of these, only one number from that. Now from that number you will try to partition the arrays into two parts. So number less than pivot will be one subarray, and number greater than pivot is another subarray. Okay, so we are not dividing the subarrays equally. We are uh, dividing the array based on the pivot element. This is called pivot element. Okay. So let's take an example here. So we have this example 24, 9, 29, 14, 19, 27. So what just we have to do is we suppose we select a pivot of 24. Okay. So that means now I have to arrange the array in such a way that all the numbers greater than 24 should come on the left hand side and all the numbers greater than 24 should come on the right hand side. So to do that, we have to traverse the array. So what our focus then will be the rest of the array. So if we have taken 24 as a pivot, then rest of the array is our focus of traversing. So what we'll do is we will check basically. So we can say that. So let's copy it down. Okay. So how we have to do is we will take one pointer of the 9. And we will take one pointer on the left on 27. So let's say left starts at 9, left pointer, and right pointer is at 27. Okay, so we will have two pointers with us. Okay, and then what we have to do is we will start comparing. So the comparison will go like this, that obviously 24 will be there. Okay, so we'll see first that left pointer whether 9 is less than 24 and whether 27 is greater than 24 or not. So mostly we look at the less part. We don't have to look at the lighter part. So we'll just check the less part. So if 9 is less than 24, that's true. We will not swap it right now. We will just keep it as it is. So once 9 is less than, we will move our pointer to the 29. That is one way of looking at it. Okay. Since you are looking at the leftmost pointer, you can start with right side as well. Okay. So so suppose if you are taking right pointer as 27, you will start from here, and then you will compare that whether 27 is greater than 24 or not. If it is greater, then keep as it is. Then you move the rightmost point. Again, you decrease the right pointer towards left. Then you will come at 19. So 19, you will see that 19 is less than 24. So in this case, you have to swap it out. So if we do like this, so it will become like 9, 29, 19, 29, 14, 24, 27. Okay. So now we came here, 24 came here, and here it is like this. Okay. Now we will start, since the left pointer is still at 9 and it came on the right hand side, so we will start our pointer from left hand side. We will start moving towards right. Then we will see that whether 9 is less than 24, correct, keep it as it is. Then we will say whether 29 is less than 24, no. So in this case we have to swap. So we swap 24. So it will become like 9, 29, 24, 14, 29, 27. So here the right pointer is still here and we are at left pointer is here. So now we will move from right pointer, we will try to move to 40. Okay, so once we have this, then we will again compare with 24. So once we compare it, we will see that 14 is less than 24. So we will swap it again, 14, 24, 29 and 27. Okay, so if we see that now since we are right side, we will try, and here's the right pointer, and we have to see whether it's left pointer. So left pointer we try to shift towards right. So whenever there's a left pointer, right pointers become equal. Left pointer value and right pointer value becomes equal. That means we have to stop. Okay, so we have got a partition, that is this highlighted one, 19, 9, 14 is less than 24, and 29 and 27 is on the right hand side. So that's how the partition will happen. And then again we try to so we divide the sub problem. So once we divide the sub problem, again the same step will follow. So 14 is one sub problem and 29 and 27 become another subproblem. Okay, once we have this, again we have to select a pivot element. That means we can take 19 or 29 just like that, and then we start comparing between each other. So once, suppose here in this case, 99 and 14, we'll find that, let's take 19 as a sub problem, so 19 as a pivot. So once we do that, after comparison, we will find that 19 and 14 sorry 14, 9 and 19, because since it's the leftmost thing, we'll start from 14. So since 14 less than 19, we'll swap it here, and then we'll check from 9, it is less than 19, we'll keep as it is. So it will become this will become a sub problem where 19 has been placed properly, and now this part of 14 and 19 14 and 9 will become another subproblem. So likewise you do till you reach to the one singular element, that is, it might be 20 or two elements, that is 19 and 4 or 27 and 29, where you compare them and you swap the element. Okay, so once you start doing it, and then you started combining them one more time. So here after doing the proper sorting, here we'll finally get a value of 9, 14 and 19, and here this is the first subarray, and the second subarray will be 27 and 29, and again you try to combine with this original array, which is 24 here, and once you do that, if you put it here 24, you'll get the final result. Okay, so that's how it works. So but how do we code it here? So I just wrote a template, and then we'll write the main logic. So template like this: we start with the main function. I give some array value. I identify the length of an array. I'll call the function called sort here, from which the quick sort will also be callable, and then finally we print the array. And this is a code for printing the array. So these are quite generic, that we don't have to write again and again. But let's start with the sorting part. So we are calling the sorting array. We are passing three elements, that is array, the low value and the high value. Okay, that is the leftmost and rightmost element position. Okay, so once we have this, the condition, like I said earlier, till we get left pointer, right pointer is equal, we have to keep on continuing. So in this case, we will just put a condition that whether the low is less than high. Once we have this, and then we'll find the partition. We are going to pass low, high, an array low and high. So this algorithm is to find the partition, that is the position of an pivot element. To find the partition position, that is the position of pivot element in the array. Okay, so when we have 24 here above, this place is properly placed because everything is less than the left, everything is greater than right. So 24 is at the proper place. So for that, we are actually finding the position of that partition place. So once we find that partition place, then we have to call it again, since we are making sub problems. So we will look at this 99 and 14 as one sub problem, right? So to call it, so we have to call them recursively. So we will write that as pi minus 1. So here the pi position will be, in this case, maybe 0, 1, 2, 3. So we are calling a subarray call from 0 to 2. That is one subarray where we are again going to find the partition, and the right subarray, that is the elements with greater than pivot, will be pi plus 1 and high. So that means what we are doing is, for 29, 27, that is from 4 and 5. For 4 and 5, we are calling again this sort function again to find the partition, such that we can get an appropriate position of the pivot element. So ideally in a quicksort, you're identifying the proper position of an pivot element and you're putting them in a proper place, and whatever the remaining will be, again you try to do the same procedure again and again. That is by finding the correct position of a pivot element. Okay. Now here, from here we calling the partition. So here the main logic will come. So this is the overall view of the quicksort. So once you find the partition, you divide the subarrays and you calling the recursively the same function sort to solving the left subarray and the right subarray. So to find that, we have to solve the partition. So in the partition, first we have to define the pivot element. In this case, we are taking the rightmost value. So rightmost element as pivot. So till now we have discussed from the perspective of leftmost, that is we are taking the first element as pivot and then accordingly we are trying to solve it. But in this code right now I am trying, we will take 27 as one of the pivot. The concept will be same. I will try to find the position of the 27 in this array in such a way that anything less than 27 will be on the left subarray and anything greater than 27 will be on the right subarray. Okay, so once we have this, and then I will create a pointer which will be low -1. So I'm just having, since we usually start with 1, so we are keeping I as the 0th value. So here it will be the index of the leftmost element. Okay, now we are going to write a array. So in this we will start with low, and if j is less than high, so we will traverse till the whole array, that is low and high, that's the this thing there, and then we will check that where ARR of j is less than equal to pivot. Okay, so again, so once we are having suppose 27 as the highest pivot, so we are going to traverse this all these things and to check whether any of these elements are less than or greater than pivot or not. If they are less, keep it as it is. If they are right, then swap the elements based on the number. Okay, so in this we will so suppose if we get since we are, so this ith is the leftmost pointer. Okay, and once if we find an element which is actually less than pivot, we are increasing its pointer to the right hand side, and then if there's a need to swap, we are swapping the element, and here are j is less than equal to pivot. Okay, so that is one thing, and then we will write a code for swapping. So in this case it will be temp ARRI and I is equal to ARRJ and ARRJ is equal to temp. Okay, so this is the one, and finally once you get a place where so again okay, once you get this place, you do with all the transaction, but you find out okay, last element, if there's a chance that we have to swap the pivot element to its original position. Okay, so in this case after traversing all, we find that 27 is actually belong to here in the place of 19. So what we have to do is we have to swap whatever the element will be present here. After doing this, most probably it will be 29 because it is less than 20, it is greater than 27. We will swap it. So error I plus 1 and error I. So it is basically to check the position for pivot. Put pivot at appropriate place, position in the array. So here again we just have to copy the swap thing, and then we just have to temp is I plus 1, this is I, and see this ARR high is the actual pivot that we have written here. We can write pivot here directly as well. highest. Okay, and we are returning the value of the AR I plus 1 because that's the position we are putting. So when if I had 27 as a pivot and I am keeping on this on the fourth position of the array, so I have to return this position of I plus 1. So once I have this, I will get this value of pi here. So in this case might be 4. So what I will do, I will create again a call a function of sort where I will divide the subarray from 0 to 3 and then 4 to 4, like that, 5 to 5. Okay, so just like that I will try to sort it. So that's how overall the idea of the quick sort. So what you have to do is first you take a pivot to find the appropriate position of the pivot by putting the elements lesser than pivot in the left hand side and pivot and any element which is greater than pivot on the right hand side, such that you will find the appropriate position of the pivot, and that will act as a partition. And from this particular position we are going to again call the sort function recursive sort till we go down to the lowest term, and then we sort the array in a appropriate time, in an appropriate aspect. That's why that means that you find a once you can get a pivot proper position of a pivot in an array, that means that that pivot is already sorted. Okay, that particular position is sorted, so you have to sort the rest of the elements. So that's how it is work. So if you try to run this array, okay, so for the array that we have taken 10, 7, 8, 9, 1 and 5, it is giving us 1, 5, 7, 8, 9, 10. So it is working properly. So if I have to again, I have to just to see how it is actually happening here is, so we are taking 5 as a pivot, and after doing some calculation, the position of the 5 would be, I'm assuming, I'm not exactly calculating here, but I will get maybe 1, 5 and maybe 1, 5, 7, 8, 9 and 10, something like that. I'm assuming here, I didn't calculate, but it will be like this. The position of fifth will be fixed, and I will get 1 as a left subarray and 7, 8, 9, 10 as a right subarray, and again I will take 10 as a, in this 7, 8, 9, 10 I will take 10 as pivot, and I will try to see how it is working. Okay, so that's all for quick sort. So if you have any question, you can type on chat, and then we will move to next sort, that is Radix sort here. Okay, I will check just message if something is there. Okay, now we will go to the Radix sort. Now the Radix sort is an interesting kind of sort because it's here we are not comparing anything. It's a no comparison sort. So we are not comparing which is bigger, which is we are not comparing between two numbers actually in this sort. But the idea comes here that the concept of bins will come into picture, and to before writing a Radix sort algorithms also in the Java, we have to understand between counting sort as well. Okay, because that's the Radix sort has been built upon the counting sort. So let's first discuss the counting sort, that is this part, and then we will discuss more in detail about the Radix sort. Okay, so here let's assume there is an array that's called 2, 5, 3, 0, 2, 3, 0, 3. Okay, now if I have to sort it, I will not start comparing. So here I need to consider only two conditions. That means I have to consider the input size and the range. The range we can consider as the value of maximum element, the max element. Okay, so what does it means here is input size here, it will be 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have input size of 8, and when I say range, it will be the 5, that is the largest value of the in the array. So that means I will consider this sorting only for the range of 0 to 5. That's it. I'm not going above, I'm not going to This is a very strict constraint that we have to follow. That's the range. So given input size 8 and I have a range of 0 to 5, I have to consider only this. We are assuming here properly that whatever the numbers will be there, it will be between 0 to 5. So that's the constraint that we are having in the counting sort. So what we are going to do here is, so once we get this range, we have to create a buckets of bins here. So that bins will represent one value for one distinct value for the particular range. So in this case, we have 0 to 5, right? So if we have 0 to 5, so we will create bins for 0, 0, 1, 2, 3, 4, 5. Now, how it will works here is, I will check each and every element and I'm going to see in which bin it should be properly placed, and I will keep a count of it. Okay, so that's how the counting thing is coming to picture. So let's start with 2. So if we have 2, we see that I get 2 here. So I will put in the bin number 2. Okay. Now I see 5. So for 5, I will keep in the bin of 5 and I will keep the count as 1. And here also count as 1. Okay. Now again I will get, then the next element is 3. So in this I will put the 3. I will keep the count as 1. So what I'm doing is just keeping the numbers according to their bins. That's it, nothing more than that, and updating the count. So once I have this, so the next number is 0 for this, then I will increase the count to 2 because we have 2 2s. One more 2, and then same case for same case for 3, and increasing the count of 3, and then again it's coming to 0. It's like this, and again we will have a count of 3. So here what we have to do is, okay, so once we get this, we arrange this array into the proper bin side sort in these bins, and we are keeping the count of it. All we have to do is, once we start getting output array, we just have to take out this bin one by one in a sequential order, maybe in this case ascending orders. So that means if I have to start with the proper count of this, so I will start with bin 0, so I will write 0, whatever it is there we will write. In bin 1 there's nothing, so we'll keep as it is, nothing to add. Then we'll add 2, that is from bin number 2. Then we'll have 3, 3, 3, that is from bin number 3. The fourth bin is 0 and 1 is 5. So that's how we are going to sort. So if you can see here, we are not comparing any number, we are just comparing number between the array elements. We are just putting them in an appropriate position. So, and we are keeping this count basically for the algorithmic aspect, because when we are going to write, we should know that how many numbers are present in that bin. So for that we are keeping this count value. Now the thing is, now this looks quite simple and just quite trivial out of it. It's quite good because the time complexity here is it's order of n plus k. Okay, so time complexity is like this, and basic that means it's a linear array, a linear time complexity, which seems to be good. But the problem here is it depends on much on the value of k. Why? Because if let's suppose in this array itself, instead of 5, if I keep 1900, so that means I have to create a bin from 0 to 1900. So that's the flaw. That means I am taking too much space. So this k is actually a kind of burden, and if k is small, it's good. It's that means it is good that we don't have to create much bins. But if it is high, then the sort may perform worse than comparison based sort. Okay, so value of k here, that is the range, matters a lot. Okay, so that is one aspect you have to look upon. Now since this k is a range, that means because of this k we are having more memory, we have to find some more optimized way. So for this, a radix sort come into picture. So what radix sort is saying that I will create the bins based on a decimal system I am having. So suppose in this we take uh, uh, an array of 10 elements, and in this the largest number is 348. So I don't have to create an bins for 0 to 348. What I will do is I will identify that what is the decimal system is. In this case it is decimal of 10, that means the numbers will be from 0 to 9. So I will create bins only for this 0 to 9, and then I will start progressing to put the elements into one bin accordingly. So there's some rules to how to put the numbers in this bin. So in this case we are just keeping 1 into 1 directly, oh sorry, 3 into 3 directly, or we are keeping 5 into 5 bin directly without even need to compare. But that's not how it works in Radix Sort. So what we have to do here is we will take a number, in this case 2000. In the first pass we will start with this, that is 237. Okay, now we will look at this, the lowest, that is the least significant digit, that is in this case the ones place, number in the ones place, that is in this case 7 in 146, 6, 9, 8, 152, 163, 235, 48, and 235 it's 5, 48 and 8, just like that. So once we have it, we will try to put these numbers into the bins according to the least significant digit. This is the first pass that we are going to have. Okay, so once we have this, so it will be like, it just you have to do AI mod 10. So once you have this, what you have to do is, let's say it's 237. So we have to keep this in 237th bin, that is in the 7th bin. Similarly, if I have 146, it will come here in 146, and then it will be 259, and then 348, and so on and so forth. Okay, so okay, let me write it properly to get a, because it will be 3 pass only. 348, and then it's 152, and it's 163, and then it is 235, and okay, let me put this in proper order. So I will just put it here. It's 48, and then it's 36, and then here it's 62. Okay, so that's how we have sorted in the first place. And then once we try to give the intermediate array out of it, we will find that we have to take in the first in first out. So we have to start with the 0th bin, and then we have to keep on take out the elements one by one. So the intermediate output would be here is 152, 62, 163, 235, 146, 36, 237, 348, and 259. That's how it's going to work. Now we can see that it's not still sorted. So what we have to do is we have to go for second pass. So in second pass, what we have to do is, now since we have already looked at the least significant digit, we will go towards more left hand side, left hand side, and check the second most least significant digit. That means in the tens place. So once we get in the tens place, again we have to solve the same process. We have to keep. So what we have to do is we have to take a number, divide by 10, and then for that whatever the output will be, for that we have to mod by 10. So for example, if I am taking 152, so if I divide by 10, I will get 15, and if I do mod 10 again here, I will get 5. So I have to keep 152 in the 5th bin. Okay, so similarly for all other process we have to do that, and the intermediate output for this will be it will be 235, then 36, then 237. I will explain I came to here directly. 146, 348, 48, 152, 259, 62, and 163. Okay, so if you observe, you have to observe the middle element here. That is, in this case, Z3, 2, 3. 3 is the 1. 3 is the 1. Here also 237, 3 is the 1. 146, 4. 348, 4. 48, 4. So in this case, when they are putting in the bins, that's how they are putting, and the final output will be like 6, 6, like this. Now still, in this case also is not is giving us much help out of it. So we have to go for the third pass. So in the third pass, what we have to see here is, since it's in hundreds, so we can divide the number in hundreds. So, and for the numbers which are in single digit or double digit, we just have to add 0 in front of it. That's it, for the better understanding. Okay. Okay. So once we have it, so for example, if I have to do this, let's take an example of 237. Okay, so 237 will be divided by 100, which will give me 2, and which is again going to mod 10, which will give me again 2. So I'm just trying to find the most significant digit in this case, and based on the most significant digit, here 0, here 0, and here also 0. So it will be kept in second bin, it will be kept as 0th bin, 2 second bin, 1 bin, third bin, 0th bin, 1 bin, second bin, just like that. So once we have this will be the final output. So what this final output will be like, if you have to do this properly and you put in the numbers, you will find it out that it will actually sort the whole array. So do this 6 2. So if you can assume y, see 036 coming first. So obviously we will put 06 in here as first. Then we put the 048 and then we put the 062. So that's why it will come like this, and then it will go for 146, then 152, 163, 235, 237, 259, and 348. Okay. So that's how the final output will come. Without comparing, we just have to see the number. We have to go from the left hand side, the least significant digit, and we have to go towards the most significant digit. And based on the values that we are giving, we have to put them in a particular bin. So that's how it will work. And this Radix sort is much better than counting sort in a way that it uses very less space, and the concept of range will here come down to the decimal system. So if instead of this 237, if I have some octal number or some hexadecimal number, based on that the bins will increase or decrease. Okay, if it's a binary number, I will have only 2 bins. If it's a decimal number, I have the bins from 0 to 9, and then based on the largest value I'm going to have, in this case I have a 348, that means it goes till hundreds. If I have 3480, in this case I have to go till thousands. So I have to take another fourth pass where I'm going to divide a number by 1000 to get the most significant digit number. Okay, so that's how the Radix sort works here. Now to code it, basically how to code it, I will just give you some rough outline of how it's going to work. We'll give, in the main function we will have an array. From that array we'll find the length of the array, we'll call the Radix sort, and we'll print the array. Printing the array is same like we just have to print an array, how we usually do. Now from Radix sort, I will first try to find the largest number. The largest number is much needed to identify that the range, till what extent we have to do a pass. So for example, I got a number of 348. So for that, finding the maximum element, finding max element from the given array. So once I find the max element, I will get an understanding that till what extent the passes it will go. So in this case, the maximum 340, that means it will go till 100 pass. It will go to 3 passes, that is ones, tens and hundreds, right? If it is in thousands, then we'll go, if it's 3480, it will go to the 4th pass, that is, it will also be in the 1000th number, right? And the concept of bins will remain the same here as it is. Now, once we have this, we will keep the counts out function, which is the on top of it is making. So, for example, when we say count, we need this number. So, in this case, the bin will be 2. In this case, the bin in the third bin it will be 1 number. In the bin 2, I have 2 numbers. That's 152 and 162. In this fifth bin, I have 1 number. In sixth bin, I have 2 numbers, that is 146 and 36. So these numbers are this count is much needed for us to understand algorithmically where we are lying. Okay. Okay, I have to do this. Okay. Okay. Let's do this. So this count number is pretty much essentially we need it, and to properly understand that how to put a number in a particular appropriate slot, that is in this case bit. Okay, and then we write a basic count sort function there, which tells that okay, once we find, like just like how we are doing here, right? We are taking AI, that is the element, and dividing by 100 or 10, and then we are taking modulus out of it. Same thing we're going to do in count sort as well. Okay, so let's start writing the function. So for this radix sort, what we have to do is first we have to find the maximum element. So find max element. For this, I am going to call a number and I'm going to call a function getMax, and I'm going to pass this array and n, that is the size of an array. Once I have this, then I'm going to call this count sort function, so which is equal to 1, and this m divided by exp greater than 0. I will tell you what does it mean, and exp is into equal to exp is into 10 into equal to 10. Okay, I'll keep like this. Okay, so what here we are putting the exp as one of the variables. What is going to do here is we start with 1. Okay, that means, and we are taking the largest value, that is here, by divided by exp, and we are checking whether it's greater than 0 or not. So, and we are increasing the exp value by always in terms of 10 in this case, because the base system is 10. So it will start with 1, then it will go to 10, 100, 1000, just like that. So if if the largest number is divided by 100, if it's still giving us a number value, that means it's more than that. So that means the loop we can call the loop. And once we have this, and then we are going to write count sort function, and then we are going to pass array, the size of an array, and this particular pointer exp. The exp is much needed for us because through this only we are identifying whether we are going from least significant digit to the most significant digit. Okay, so we'll write the count sort, but first let's write the getMax function, which is very easy to write. That is just to find the maximum element in the array. So I'll just write it down for int I equal to 1, I is less than n, I plus plus, and I just checking if ARI is greater than mx. If it is greater, then you just make the maximum value of that ARI. Okay, and then you just part the maximum value. Okay, so here this finding maximum element will be it's quite easy just to find the maximum element. We are comparing each and every number. But now the main thing will come to the count sort. So here we are going to make some few auxiliaries arrays to keep our intermediate and the final output array. So this is not an in-place sort, this is external sort. So this is the output array, and then we're going to create a pointer called I, and then we're going to create bins. In this case I'm giving them a count for better understanding. New 10. Okay, now count this bin based on the 10 I'm giving based on the decimal system. Here we know that's 10. We are mostly having the decimal system, that's why we are giving 10. Based on the number system that you're having, you can change the value. So we are going to, this count array will be exactly this bin. So in this we are going to see that how many, for a particular bin, how many elements can be stored. Okay, so we're going to keep that as a pointer. Okay, and for arrays dot fill count 0. Okay, so what I'm doing here is I'm just for this count array I'm initializing every bin with 0 value. So here the every value here it will be 0. So for that I'm initializing the 0 value, and then now I have to store that where I will check the occurrence, check each element and store the occurrences in count array. So just like what we are doing, right? We are taking an element, we are modulus by 10, or first we are taking an element divided by 10, and then we are taking modulus. So based on the position of the element, we are finding the occurrences that we are going to have, and then we are just storing the numbers in that particular count array. So I just take I equal to 0, I less than n, and I plus plus, and then I'm just going to write count. I'm going to be here a little tricky here. So ARRI and multiply EXP, and I'll just keep it here just like this, and mod by 10, and I'm just keeping plus plus. Okay, so what does it mean here? So what I'm doing, exp in our initial case will be 1. So exp here is 1. So if I'm taking 157 as ARRI is equal to 157 and exp is equal to 1. So what I'm doing, I'm taking the least significant digit, that is in this case 7. So I have to identify that. So what I have to do is 157 divided by 1 and then modulo 10. If I do that, I will get the value of 7. So on the 7th position of the count array, I will increase the value by 1. So that means there is a one element called 157 which is put in the bin of 7th. Okay, so in this case, in the first case also, or let's say 237 instead of 157. So this instead of 237, 157 will be there, and I'm increasing count by 1. So that's what we have written here. So once we found the occurrences just like that, now we have to okay, now we have to do a little more processing in this count function to such that it contains the actual position of the digits. Okay, so we have just taken the count, but we also have to look at the actual position. That is, if we are taking 157 as number, I should know where it should be kept for the intermediate results. So for to do that, I will start with, again I will write a for loop. I will write till 10, I less than 10 and I plus plus. Once I have this, and then I will just write count I plus, this is for count I minus 1. Okay, so to give an example for this, what does it mean? Okay, so what does it mean? I will just show you through this example of counting sort, because that's what we have taken here, right? So we have this. Okay, let's take this bin 1. We have written here. Okay, so we have this bins, and we have this array as well. Where is the array? Okay, let's keep it here. 0 is number 3. Okay, 3 2 7. 3D715. Okay. Let's take this as it is, and then we'll put it here. Original array. So it will be like this. Okay. So what does it means here is I have to know that from which position the count from which position to which position it is taking the particular value. That means, for example, in this is the 0th bin and this is the first bin is empty. Okay, so here also I will write 2. Okay, for the first bin. Now now in the second bin, that is 2, I found that 4 numbers are actually before me, and then in this 4 to 6, then it will go to 6, and this is 7 position. Okay, so now again to reiterate back what does it means. So I'm trying to keep a position out of it. So if I have bin equal to 0, this is 1, this is 2, this is 3, this is 4, this is 5. These 5 bins are there, right? Now what we are doing here is, till the position 1 and till we get this 2th position, right, the actual bin 2, therefore there will be 4 numbers between till 2 that we can find. So if you can see the final output also, I will just paste it down in this case. Okay, so this is much needed. So at position 2, for the bin 2, we will have 4 numbers. So that means these 4 numbers will be there, and then till 3rd bin I will get 6 numbers out of it. Okay, sorry, in this case, yeah, numbers will be 3, right? So I'm sure it's 7 and 8. So since we have 4th value, so till 4th position bin I will get all the values which comes under this bin 3 and less than that, and the final value with that is 8 will be kept at the position 8. So this it is keep as a track to keep the position that for the particular bin from 0 to this point this much amount of number should be there. Okay, so for actual to know the actual position of the digit, actual numbers, we are keeping this track. Now once we have this, we have to build the output array. So once we have, so what we have to do is, for I, we are starting from the behind, and because we will look at from here, so we will, whatever the number will be put at the bin 5, I will take this as a number and I will try to put in the proper in the final output array, and I will go from the behind 0 I plus plus, and what I will do is output, and I will take count. So again I will take ARRI, EXP, and this will be modulo 10, and this will be -1, so it will be ARRI. Okay, and count of, you don't have, this is a little tricky one, you might have to remember also, this might chance that you have to remember, exp modulo 10, but if you understand the logic, it's quite simple. Okay, so what we are doing here is, for the output array, we are taking this ARR value, that is the actual element of the array. From that array, we are finding that in which bin it will be. So based on that, we identify the bin number. So based on the bin number, we will assign the particular position of that for this value, and then we will reduce the value by 1. In that particular bin, we will reduce if it is the bin has 2 numbers in that, so I will reduce that bin number from 2 to 1. So what does it mean is, suppose I have 3 here. Okay, so till position 7 I can still have 3. So once I have 3, what I will do, I will put 3 in this 7th position, and I will reduce the 7 value with 6, just like that, to get an understanding, to have a proper understanding that from where we are starting and where we should keep the number. Okay, so once we have this also, so what at the end we have to just put, we just have to copy the find output array to the original array. This is the last step that we have to do, and we just have to do this for I equal to 0, I less than n, I plus plus, and then arr I equal to output I. So we are just keeping this value, and that's how it will be happening. Okay, so let's run this, and I will quickly again go through the what is Radix Sort meant to be. So for this given array of this much, let's see how whether it will work or not. Okay, so I got some errors at 82, 97 and 1111. 1111, that is arrn, and 82, that is in this case is this. I have this, I have this. Okay, so here the some expression thing has happened. I have this arrI, and 97 also has some problem, and it's by p, it's by 10. Okay, start with 1, count sort is like this. Okay, let's see, let's run it one more time. Array out of bound. Okay, so I'm doing something. Oh, I should do minus minus here. My bad. Okay, I think it should run perfectly fine now. Okay, now it's 225. Okay, it's perfectly sorted the numbers. Okay, so this code is working. So let's go through one more time to understand. It's a little easy to understand, but it's little complicated to when you write the code. Okay, so what we are doing is it's built, the Radix Sort is built upon the counting sort. That means we'll make bins, and based on the numbers, we'll particular element, we will put the particular element in the appropriate bin. So in Radix Sort, what we are doing is we are actually dealing with the number of the positions. So we are looking at a number, we are dividing them from least significant digit to the most significant digit, and then we are keeping them in appropriate bins in each pass, and till we reach the last pass, that is the most significant digit, we'll identify that we'll get the final output as a sorted output. So what we are doing here is we are calling function called Radix Sort. Here we are first trying to find the maximum number, which is much important to identify that how many digits will be there in a particular element. So if the largest number contains 4 elements, that means we might have 4 passes. Okay, then we are calling the count sort function, where we are dealing with since we are dealing with the positions, we are starting with position ones, then we'll keep going to tens, then hundreds, then thousands, so on, based on the maximum element value. So based on that, we are calling this, we are increasing the value of exp, and then we are calling this count sort function. In count sort function, we are creating two auxiliary arrays, that is, one is output array and one is count array. The count array is basically a bin array where we are keeping the number, we are keeping the count of which, how many, for a particular pass, how many numbers belongs to a particular bin. So we are keeping account for that. Now once we have this, we start checking each and every element of an array, and we fill the count array based on that. So just like how we are seeing here, we take an array, and here for the particular each bin we are counting the number of elements it might have, right? So this is the one aspect. Now the second aspect after having this is, and this is a much crucial aspect here, is we are counting the positions. So once we get the for each and every bin, we are finding that okay, this many numbers are fitting in that bin. We have to see the position till what number the bin's number will actually assign in the output array. So just like we have seen here, that for the number for the bin 3 till 7th position, I can fill the number. Okay, for the bin, for the fifth position bin 5, I can only put that number, and I can put the element only at the particular position at the 8th position. So I'm keeping a track of all those stuff. Once we have this, I will try to build an output array, where again what I'm trying to do is I am taking the number, I'm dividing it by a particular position place, and then I'm modeling by 10 to give a particular bin value, that is the last element or the middle element, just like that. And once I have it, I will keeping them in an output array, and once I kept them in output array, I'm reducing the count array value of that particular bin by -1. And once I have this, I will create an output. I will print, copy the output array values in their origin array. So this is the this is how this radix sort works. It is a non-comparison sort, and it is also, its time complexity is n plus k, same as counting sort as well. But here the k value will be actually quite restricted to the base of that element. So here k will be in the terms of base, maybe log of n, where we're trying to find the particular base. So in this case the base will be 10, so we will create 10 bins out of it, because we are using a decimal number system. So it's quite fast, and it's quite used also in our computer system, in our particular computer applications as well. Okay, so yeah, so that's the, so I will stop the sharing. Okay, so that's the overview of the sorting function that we have seen till now, and that's the end of the session. So if you have any question, you can ask me. Otherwise, I'll just stop the meeting as well. Just